This is an example of a two-sample t-test, which is a hypothesis test between two population means for independent samples when the standard deviations are unknown. The population standard deviations are unknown. And in this example, we're assuming that the population variances are unequal. Many studies have been conducted to test the effects of marijuana use on mental abilities. In one such study, groups of light and heavy users of marijuana in college were tested for memory recall with the results given below. Use alpha equal 0.01 to test the claim that the population of heavy marijuana users has a lower mean memory recall than the light users. And again, I'm assuming that the population variances are unequal. So I have the summary statistics here, the summary information for the heavy marijuana users and the summary information for the light marijuana users. So I need to write the claim as a mathematical statement in terms of mu sub 1 and mu sub 2, and then structure the null and the alternative around that. So the claim is that the population of heavy marijuana users has a lower mean than that of light users. And I've already labeled the heavy user sample as sample 1. So that would be mu sub 1 less than mu sub 2. The heavy marijuana users has a lower mean than the light marijuana users. So I can move mu sub 2 over to the other side using subtraction, and I'll have 0 on the right side. And because this does not contain the case of equality, this is my alternative. So my null statement is that mu 1 is equal to mu 2, okay, or mu sub 1 minus mu sub 2 is equal to 0, versus mu sub 1 minus mu sub 2 is less than 0. So this is the claim. Now, this is a two-sample t-test and for independent samples, and the test statistic is a little cumbersome to input the information into. Specifically, if you wanted to do this by hand, it would be x bar sub 1, x bar minus x bar sub 2 minus 0, the claimed difference from the hypotheses. Now, when we're assuming the variances are not equal, that denominator isn't as messy as when we are assuming they are equal. So the denominator would be the sample variance for the first sample over the sample size plus the second sample variance over its sample size, all under the square root. So it's very similar to the two-sample z-test for independent samples, but you just use the sample variances in the denominator. But I'm going to go ahead and get the standardized test statistic and p-value using the TI-84. Before I do that, though, I'm going to go ahead and find the critical value. I will have only one because this is a lower tail test. And when we're assuming the variances are not equal, for the degrees of freedom, we're going to use the smaller of n1 minus 1 or n2 minus 1. So basically we just look at the sample sizes. Which one is smaller? Well, this one. So my degrees of freedom for my critical value is going to be 39 because the smaller sample size is 40. It's a lower tail test, and I'm using a level of significance of 0.01. So drawing a bell-shaped T distribution, shading in my lower tail, area of rejection, level of significance is 0.01. I expect that critical value to be negative. Degrees of freedom is 39, and this table that I'm currently using is, I just have to say, the font is just way too small for someone my age. Even with my bifocals. All right, so reading over to point 0.01. Now I know the table indicates an upper area. The table only gives the positive values, but we know by symmetry that anything below 0 will just be opposite in sign. So 0.01 amount of area in that tail, looking down to 39 degrees of freedom. And I don't have a 39 in this table, so I can just go ahead and look at this one here. I'll go to 40. So my critical value is approximately negative 2.423. I can get that critical value a little more accurately, although that's probably very close, using my inverse t in my calculator. Going to the distribution menu, selecting option 4. The cumulative area to the left of that critical value is 0.01. Degrees of freedom is 39. So it's a little bit different. The thousandth place is off. Okay, but if we were rounding to 2 decimal places, it would be the same. So using the TI-84, so inverse t, this critical value is negative 2.426. Okay, so very close. Okay, it's really not going to make a big difference in our decision of whether to reject or fail to reject the null. All right, so now that we have our critical value, we need to see where our standardized test statistic is placed along this horizontal axis. Again, instead of inputting into the formula, I'm going to go to my stat menu in the calculator, over to tests, and option 4 is the 2-sample t-test. I have the summary statistics, and I just need to change the values. Okay, so my first sample size was 51.3, sample standard deviation 4.5, sample size 46. Second sample information, 53.3 for the sample mean, 3.6 for the sample standard deviation, 40 for the sample size. And now I need to change the the alternative to be a lower-tailed test or a left-tailed test. Now, you'll need to change this depending on whether or not you're told to assume the variances are equal or you're assuming the standard deviations are equal. When they're assumed to be equal, you select yes for pooled. Okay, that's going to give the test statistic with that longer denominator. When the variances are not equal, then you're going to select no. And then calculate. So my standardized test statistic is negative 2.288. Okay, so putting this off a little bit to the side. So using the critical value method, deciding where it's placed, negative 2.288 is very close to our our critical value, but it is not further to the left in the rejection region, but it's close. Okay, so the test statistic is about here. So using a level of significance of 0.01, the decision is to fail to reject the null. Okay, so if we fail to reject the null, you can think of it as the null is the winner. Notice I did not circle the claim. So to state our conclusion, there is not enough evidence or there is insufficient evidence to support the claim that the population of heavy marijuana users has a lower mean memory recall than that of light users. Now let's take a look at the p-value. The p-value is going to be the area further to the left of our standardized test statistic. So our p-value going back to my calculator, is 0.0123. Okay, that's the area further to the left. And comparing that to our level of significance, 0.0123 is just a smidge greater than 0.01. So the decision would be to fail to reject the null, which is the conclusion we came to with the critical value method. But if we changed our level of significance to 0.05, the more common level of significance, our decision would now change. 0.0123 is less than 0.05. So if our level of significance was 0.05, the decision would be to fail to my apologies, the decision would be to reject the null, and then at that level of significance, there would be sufficient evidence to support the claim.